Hello, everyone. Thank you for attending a new lecture of our PIM course. Today, we have a special speaker, a special guest speaker. She's Christina Giannoula. She's a PhD student at the National Technical University of Athens, and she has been working with the Safari Research Group for quite a long time already. And she is a lead author of this Sparse paper and library as well. That is the first implementation of sparse matrix vector multiplication on a real processing in memory architecture. I think it's a very interesting work, not only because it targets a key primitive for many important applications, but also because she reveals what are different things that still need to be optimized in processing in memory systems to make them even better for these kind of interesting primitive. So Christina, if you are ready, thank you very much for the talk. Feel free to start.
Thank you for the introduction. Okay, so let's start. So in this talk, I will introduce Sparse P, the first sparse matrix vector multiplication library for real processing memory architectures. This work will appear at the SpMatrix conference in the beginning of June, in a few weeks. Okay, so in this work, we have designed the first sparse matrix vector multiplication software package for real processing memory architectures, and we call it Sparse P. Sparse P is publicly available and open source in order to enable further research in the SpMV kernel and in future processing memory systems. And then we also provide the first extensive study of the SpMV kernel on the first real-world and commercially available PIM system. This study leads to many recommendations for architects and software designers of PIM systems. So I will start with the motivation of this work. Sparse matrix vector multiplication, or SpMV, is a fundamental linear algebra kernel and lies at the heart of many important applications from the scientific computing, graph processing, and machine learning domains. However, in commodity systems like CPUs and GPUs, it has been repeatedly reported to achieve only a small fraction of the peak performance of the system, and it is primarily bottlenecked by the memory bandwidth of the system. At the same time, several manufacturers have started to commercialize near-bank processing memory or PIM systems. A processing memory or PIM system consists of multiple PIM-enabled memory modules connected to a host CPU via common channel-based connections. Each PIM-enabled module supports several PIM cores. Each PIM core is located close to a DRAM bank. And as a result, these real PIM systems can provide high levels of parallelism, low memory access latency, and large aggregate memory bandwidth, thereby being a very good fit to accelerate the SpMV kernel. A few real near-bank PIM architectures are Samsung's VMDRAM, the SK Xilinx AM, and the UPMEM PIM system. To this end, we make two key contributions. First, we designed Sparse P, the first SpMV library for real PIM architectures. We proposed 25 efficient SpMV kernels supporting several compressed matrix formats, data types, data partition techniques, load balancing schemes, and synchronization approaches in order to cover a wide variety of matrices and applications. And second, we conduct a comprehensive study of the popular SpMV kernel on the first commercially available real PIM system, the UPMEM PIM system. Our characterization study includes a wide range of sparse matrices with diverse characteristics and comparisons to state-of-the-art CPU and GPU systems. Our analysis provides many recommendations for software, system, and hardware designers. So let's first take a look on the SpMV kernels that we support in the Sparse P library. In order to execute the SpMV in a PIM system, we can the end-to-end SpMV execution can be broken down in 4 steps. First, we have the time to load the input vector into the DRAM banks of PIM-enabled memory. Second, the time to execute the SpMV kernel using the PIM cores. Third, the time to retrieve from DRAM banks to the host CPU the results for the output vector. and for the time to merge partial results and assemble the final output vector on the whole CPU. Our evaluated system does not have PIM-enabled memory as the main memory of the system, and thus we'll need to load the input vector to the PIM-enabled memory modules. However, our kernel implementation would be the same and could be applied to an architecture where the PIM-enabled memory constitutes the main memory of the system, and therefore the step 1 could be avoided. To parallelize the SpMV kernel, SparseP supports two general types of data partitioning techniques. First, we provide an anti-partitioning technique where the matrix is horizontally partitioned across PIM cores and the whole input vector is copied into each DRAM bank of each PIM core. And second, we provide a 2D partitioning technique where the matrix is partitioned in 2D tiles. The number of tiles is equal to the number of PIM cores used. With the anti-partitioning technique, almost the entire SpMV computation is performed using only the PIM cores, since PIM cores directly compute the final elements for the output vector. However, with this scheme, the input vector needs to be replicated at each DRAM bank of all the PIM-enabled memory modules, and thereby the number of copies of the input vector that is transferred from the whole CPU to the PIM-enabled memory modules through the narrow memory bus is equal to the number of PIM cores used. With the 2D partitioning technique, we aim to strive a balance between computation and data transfer costs, since only a subset of the elements of the input vector is copied into the DRAM bank of each PIM core. Therefore, the number of copies of the input and output vectors that are transferred to and from PIM-enabled memory modules through the narrow memory bus depends on the number of vertical partitions that we create in the 2D partitioning scheme. In the one partitioning technique, we provide various load balancing schemes among multiple PIM cores for the four most widely used compressed matrix storage formats. For CSR and Q formats, we load balance either the number of rows or the number of non-zero elements across PIM cores. For BCSR and BQ formats, we load balance either the number of blocks or the number of non-zero elements across PIM cores. However, the load balancing depends on the characteristics of each compressed matrix format. More specifically, in the CSR format, since the matrix is stored in row order, load balancing of the non-zero elements across PIM cores is limited to be performed at the row granularity. In contrast, in the Q format, the matrix is stored in non-zero element order, and therefore load balancing of the non-zero elements can be performed by splitting a row across two neighboring PIM cores, and therefore we can provide a near perfect non-zero element balance across PIM cores. Similarly, the BCSR and the BQ formats are the block-based counterparts of the CSR and Q formats respectively, and therefore in the BCSR, again, the load balancing is limited to be performed at the block row granularity. So in the 2D partitioning technique, SparseP supports 3 schemes for all the 4 compressed matrix formats mentioned. First, in the equal size scheme, the 2D tiles are statically created to have the same height and width. This way, the subset of the elements for the input and output vectors have the same sizes across all PIM cores. However, this scheme has high non-zero element imbalance across the PIM cores because we create static partitions on a very sparse matrix. Second, in the equally wide scheme, the 2D tiles have the same width and variable height. For each vertical partition on the matrix, we load balance the non-zero elements across the tiles of the same vertical partition. In this scheme, the subset of the elements for the input vector has the same size across PIM cores, while the subset of the elements for the output vector varies across PIM cores. And in this scheme, we can provide high non-zero element balance across the PIM cores of the same vertical partition. And finally, in the variable size scheme, the 2D tiles have both variable width and height. In this scheme, we load balance the number of non-zero elements both across the vertical partitions and also across the tiles of the same vertical partition. And as a result, we can provide high non-zero element balance across all PIM cores. Moreover, since real PIM architectures can support multi-threaded PIM cores in both the 1D and the 2D partitioning techniques, we support various load balancing schemes among threads of a single multi-threaded PIM core. In this example, in the left sub-figure, we can see that for each PIM core, we create a smaller matrix, a smaller sparse matrix, and then we can load balance the number of rows across the threads of the multi-threaded PIM core. Similarly, in the 2D partitioning, we can still we also create smaller sparse matrices that are in those sparse matrices we can load balance the number of rows across multiple threads of a single PIM core. And we support both various load balancing schemes, like either balancing the number of rows or balancing the non-zero elements across the multiple threads of each multi-threaded PIM core. In a Q format, as I mentioned, as I mentioned in the load balancing across multiple PIM cores, the load balancing across multiple PIM threads can also be performed by splitting one row across two neighboring threads of the same core. And in this case, we need to have synchronization. We need to implement synchronization among the multiple threads of the same PIM core. And as a result, SparseP supports various synchronization approaches among multiple threads of a single PIM core. More specifically, we provide three different synchronization approaches. First, we have the coarse grain loading approach, in which one single global mutex protects all the elements of the entire output vector. Second, we have a fine grain loading approach, in which multiple mutexes protect the elements of the output vector. In our evaluation, we use 32 mutexes, which are associated to the elements of the output vector in a round-robin manner. And finally, we have experimented with a log-free approach, in which threads create partial results that are temporarily stored in a data scratchpad memory, and later one single thread merges these partial results and writes the final result for the particular element in the local DRAM bank. Overall, SparseP provides 9 1D partition kernels and 16 2D partition kernels, and it is publicly available on GitHub. For the CSR and BCSR formats, load balancing across PIM cores and across threads within a PIM core is limited to be performed at a row and block row granularity, respectively. And for the Q and the big Q formats, in the load balancing among the multiple threads of a single PIM core, we need to implement synchronization, and we have 3 different synchronization approaches that can be supported in all the different data partitioning techniques. Finally, all these kernels support a wide range of data types, including both low precision integer and also high precision float data types. So let's now take a look on the most important key takeaways of our analysis. This is the real UpMem PIM system that we use in our evaluation. It includes 20 UpMem PIM DIMMs that are connected to a host CPU, and we have in total 2,560 PIM cores. Each PIM core is located close to a DRAM bank and can support up to 24 threads. These threads share a 24 kilobyte instruction memory and a 64 kilobyte data memory, and all threads can access data from a local 64 megabyte DRAM bank by performing read and write transactions through a DMA engine. We evaluate a wide variety of sparse matrices from the Switch Sparse Matrix collection. When the standard deviation of the non-zero elements across rows and columns of the matrix is low, the matrix is referred to as regular. However, when the standard deviation of the non-zero elements across rows and columns is high, the matrix becomes very irregular. It has a power law distribution, and it is referred to as scale-free matrix. So we first examine the kernel time only of the SpMV execution using only one single PIM core. In this figure, in this experiment, we compare the performance of the fine-grained locking scheme over the coarse-grained locking scheme using multiple threads on a single PIM core. In this experiment, we use 16 threads on a single PIM core. And what we observe is that the fine-grained locking approach does not improve performance over the coarse-grained locking approach. This is because the DRAM accesses of multiple threads are performed as transactions in the UpMem PIM hardware. These transactions are serialized in the DMA engine of each multi-threaded PIM core, and therefore they are performed in a serial manner, and the critical sections, even though they might work on different locations in the local DRAM bank, those critical sections are serialized, and as a result, the fine-grained locking approach cannot increase the parallelism. So we conclude that the fine-grained locking approach to parallelize critical sections, it cannot improve the performance over the coarse-grained locking approach when the PIM hardware does not support concurrent accesses to different locations of the local DRAM bank. To this end, we recommend architects of PIM systems to provide low-cost synchronization approaches among multiple threads, and also to provide hardware support to enable concurrent memory accesses by multiple threads to the local DRAM bank. And also another approach would be to integrate multiple DRAM banks per PIM core, and therefore multiple threads can access different banks, different DRAM banks, local DRAM banks concurrently, and as a result, we could increase the execution parallels. Next, we compare the load balancing of we compare two different load balancing schemes. First, the load balancing of the number of rows versus the load balancing of the number of non-zero elements across multiple threads using the CSR and the Q formats for the left and the right plot respectively. We observe that the load balancing of the non-zero elements performs better than load balancing the rows in most of the matrices. And this is because load balancing the number of non-zero elements typically creates higher computation balance across the threads of a single multi-threaded PIM core, and it achieves higher performance. However, we find that in a particular matrix, in Delaunay matrix, load balancing the number of non-zero elements creates high row imbalance among the threads of a PIM core, because only one single thread processes a significantly higher number of rows compared to all the remaining 15 threads. More specifically, in this particular matrix, due to the row imbalance, only one single thread performs a much higher number of memory accesses for the CSR and a much higher number of synchronization operations in the Q format, for example, compared to all the remaining 15 threads, and therefore this creates high performance overheads in the PIM core pipeline. So we conclude that high operation imbalance among threads of a compute-bound PIM core can incur high performance overhead, and as a result, we recommend the programmers to provide intelligent algorithms that provide high load balance across the threads of a PIM core in terms of the computation, the synchronization points, and the memory accesses for each particular input given. And finally, in these experiments, we present the scalability of all the compressed matrix formats as the number of PIM cores increases for a variety of sparse matrices. Even though an UpMem PIM core can support up to 24 threads, we observe that the SpMV execution for all compressed formats typically scales up to 12 or 16 threads. And this is because the pipeline of the UpMem PIM core is fully utilized whenever we have 16 threads, and therefore, if we further increase the number of threads, we cannot get a better performance. So next, we examine the kernel time of the SpMV execution using multiple PIM cores and having 16 threads per PIM core. In this experiment, we compare the 4 compressed matrix formats by normalizing their performance to that of the CSR format. In the one-to-partition kernels, we find that in scale-free matrices, Q and BQ formats significantly outperform CSR and DCSR formats respectively. This is because Q Q and BQ formats provide higher non-zero element balance across PIM cores, since CSR and BCSR formats are limited to perform load balancing at a row and block granularity, respectively. We observe similar behavior in the 2D equally sized kernels. In the 2D equally sized kernels, even though all the compressed matrix formats have the same non-zero element balance across the PIM cores, because we create static partitions, static tiles on the sparse matrix, the number of the non-zero element balance among multiple threads of a single multi-threaded PIM core is affected by the compressed matrix format used. And as a result, Q and BQ formats outperform CSR and BCSR formats, especially in scale-free matrices, because they provide high non-zero element balance among threads of a single multi-threaded PIM core. And finally, in the 2D equally wide and 2D variable size schemes, we find that Q and BQ formats significantly outperform CSR and BCSR formats across all our evaluated matrices, both in regular and also in scale-free matrices. This is because Q and BQ formats provide higher non-zero element balance across PIM cores and also across threads within a PIM core. So our main key takeaway from this analysis is that the compressed matrix format used to store the input matrix determines the data partitioning across the DRAM banks of the PIM-enabled memory module, and therefore it affects the load balance across the PIM cores with the corresponding performance implications. As a result, we recommend software designers to propose compressed data structure for sparse kernels that can be effectively partitioned across DRAM banks with the goal of providing high computation balance across PIM cores and also across threads of a single PIM core. So before going into the end-to-end characterization analysis, I think I can pause here and I can ask if there are any questions until now.
Thank you, Christina. I don't see any questions in the YouTube chat. I would like to remind everyone attending in YouTube that they can type their questions there, and we will gladly convey them to you. I also don't think there are any questions from people attending in Zoom, but feel free to ask if you have any. If not, I think you can continue, Christina.
Okay, great. Okay, so next we will characterize the end-to-end SpMV execution, meaning that we will see some performance results on the SpMV execution when we account and we include the data transfer cost for the input and the output vector whenever we accounting the time in order to transfer the elements of the input vector and the elements of the output vector and merge the final results on the whole CPU. So first, we evaluate the scalability of all data partition techniques as the number of PIM cores increases. Performance is normalized to that with 256 PIM cores. First, we find that the scalability of the 1D partitioning technique is limited by the load data transfers because the amount of bytes that is transferred to PIM-enabled memory for the input vector grows linearly to the number of PIM cores. As I mentioned, the input vector needs to be replicated at the local DRAM bank of each PIM core, and therefore a high amount of bytes is transferred from the whole CPU to the PIM-enabled memory modules through the narrow memory path. So we conclude that the 1D partition kernels are bottlenecked by the high data transfer cost to broadcast and replicate the whole input vector into each DRAM bank of all PIM cores. So to this end, we suggest hardware and system designers to optimize the broadcast collective in data transfers to PIM-enabled memory in order to minimize the overheads of copying the input data into all DRAM banks of the PIM system. Second, we find that the 2D equally sized scheme, in the 2D equally sized kernels, the kernel time limits the scalability. We find that the kernel time of those schemes is limited by only one PIM core or only a few PIM cores assigned to the static 2D tile with the largest number of non-zero elements, which in turn affects the scalability of these kernels. And finally, we find that the scalability of the 2D equally wide and variable-sized kernels is limited by the retrieve time to transfer the results for the output vector from PIM-enabled memory modules to the host CPU. These schemes are severely bottlenecked by the high amount of padding with empty bytes performed in the parallel data transfers to retrieve results for the output vector. More specifically, our evaluated system supports parallel transfers at a rank granularity, meaning among 64 PIM cores, and therefore we need to perform and implement a high amount of zero padding, with empty bytes in the retrieved data transfers, and this amount of padding accounts for approximately the 88% of the data transferred from PIM-enabled memory to the host CPU, thereby creating high bottlenecks in the narrow memory bus. And as a result, we conclude that the 2D equally wide and variable-sized partitioning schemes require fine-grained data transfers to be supported at DRAM bank granularity to be supported in the PIM system, having zero padding in order to achieve very high performance. And therefore, we suggest hardware and system designers to optimize the gather collective operation from PIM-enabled memory to the host CPU and provide parallel data transfers at DRAM bank granularity, having zero padding, in order to significantly minimize the overheads of retrieving the final output results on the host CPU. And then next, in these experiments, we have experimented and we check the end-to-end performance on various sparse matrices and later on two different processing memory systems. When we compare different sparse matrices in the 1D partitioning scheme, for example, we observe that for the Hugetric and L-Dur matrices, the best end-to-end performance is achieved using 64 and 128 PIM cores, respectively. In other words, the number of PIM cores that provides the best end-to-end SpMV performance depends on the characteristics of the input matrix, depends on the particular sparsity pattern that we have in the input matrix. And we have seen similar results in the 2D partition kernels. In this particular example, in this particular experiment, we have a fixed number of PIM cores, which is 2048 PIM cores, and we vary the number of vertical partitions from 1 up to 32 vertical partitions in the 2D equal size kernels. For the various sparse matrices, the performance is achieved using a different number of vertical partitions. For example, in Hugetric and MM-chip matrices, the best performance is achieved using 16 and 8 vertical partitions, respectively. In other words, the number of vertical partitions that provides the best end-to-end SpMV performance depends on the sparsity pattern of the input matrix. And in this experiment, we evaluate the same matrix, the SpMV performance using the same matrix and using two different PIM systems, the characteristics of which are shown in the table. In the PIM system A, we have cores with 350 MHz frequency, and in the PIM system B, we have 2048 cores with 425 MHz frequency. So in this experiment, we find that for two different PIM systems, the best performance is achieved using a different number of vertical partitions. In other words, we find that the number of vertical partitions that provides the best end-to-end performance depends on the characteristics of the underlying PIM hardware, or depends on the characteristics of the PIM system. And based on the last three experiments, we conclude that there is no one-size-fits-all parallelization approach for the SpMV in the PIM system, since the best end-to-end SpMV performance of each parallelization scheme depends on the characteristics of both the input matrix and also the characteristics of the underlying PIM hardware. Therefore, we recommend programmers to design adaptive algorithms that tune their configuration to the particular patterns of each input given and also to the characteristics of the underlying PIM hardware. And finally, we compare all data partitioning techniques. And in this experiment, we ran many different configurations for each data partitioning technique. For the 1D partition kernels, we vary the number of PIM cores from 64 up to 2,528 PIM cores. And for each matrix, we select the best performing end-to-end execution throughput. For the 2D partition kernels, we use 2,528 PIM cores, and we vary the number of vertical partitions on the matrix from 2 up to 32 partitions. And for each matrix, we select the best performing end-to-end execution throughput. So we find that across all matrices, the equally sized 2D partition technique performs best in regular matrices, while the 1D partition technique performs best in scale-free matrices. However, we find that in both techniques, the best end-to-end performance is achieved a much smaller number of PIM cores than the available PIM cores of the system. There are many idle cores in the system because the best performing SpMV execution is a trade-off between computation and data transfer costs through the narrow memory path. So we conclude that the expensive data transfers to and from PIM-enabled memory modules performed via the narrow memory path impose significant performance overhead to the end-to-end SpMV execution. And as a result, it is very hard to fully exploit all the available PIM cores of the system. To this end, we recommend software, hardware, and system designers to provide high-speed communication channels and optimized libraries in data transfers to and from PIM-enabled memory modules, to provide hardware support to effectively overlap the computation with the data transfers in the PIM system, and also to integrate the PIM-enabled memory as the main memory of the system in order to eliminate the load data transfer costs in sparse kernel executions. And finally, we compare the SpMV execution on the UpMem PIM system with that of a common CPU system and also a GPU system. In the GPU system, we also account for the time to transfer one instance of the input vector to the GPU global memory, from the main memory to the GPU global memory, and also the time to retrieve the final output vector to the host CPU. So common CPU and GPU systems are processor-centric systems with high computation capabilities, while real PIM systems are memory-centric systems with high bandwidth capabilities. So when we consider only the actual kernel time without accounting for the data transfer costs, we find that the SpMV kernel execution on a real PIM system achieves a much higher fraction of the peak performance compared to that of CPU and GPU systems, thereby providing a much higher total cost of ownership and higher resource utilization. Instead, when we consider the end-to-end execution, including the data transfer costs, the data transfer overhead for the input and output vectors, we find that the CPU system performs best. However, PIM systems are still maturing, and future PIM systems are expected to reduce the data transfer costs, for example, by integrating the PIM-enabled memory modules as the main memory of the system, or by providing hardware support to overlap the computation with the data transfer costs in order to hide the latency. And regarding the kernel SpMV energy, we find that the GPU provides the highest energy efficiency, while the 1D partition kernels can provide better energy efficiency on the SpMV compared to the CPU system. For example, in the floating point data types, even though they are not supported by the PIM hardware, the SpMV execution on the PIM system provides 1.38 times less energy consumption, higher energy efficiency over the GPU system average across all our matrices. So we conclude that the PIM system can potentially provide high energy efficiency on the sparse kernel. So please refer to our full archive paper for many more results, key insights, and key takeaways. So let me now conclude my presentation. Sparse matrix vector multiplication is a fundamental linear algebra kernel and is used in many important applications. However, in commodity systems like CPUs and GPUs, it is highly bottlenecked by data movement between processor memory. Real near-bank PIM systems can tackle the data movement problem by placing low-area cores very close to DRAM banks. PIM systems provide high levels of parallelism and large aggregate memory bandwidth, thereby being a very good fit to accelerate the SpMV kernel. To this end, we have designed the first open source SpMV library for real PIM systems, which is called Sparse P, and it is publicly available on the GitHub link at the end of this slide. And we also provide the first comprehensive characterization study of 25 efficient SpMV kernels on the first commercially available real PIM architecture. Our work provides many new insights and recommendations for software designers and also hardware architects in order to improve multiple aspects of future PIM software and hardware. For more details on our work, we invite you to read our full archive paper. Thank you so much for your attention, and I'm happy to take questions.
Yeah, thank you very much, Christina. Very good talk. I think everything was very clear. I don't see any questions in the YouTube chat yet. I don't know if there are any questions from the audience in Zoom. If not, I have a couple of questions for you.
Sure.
Okay, so I will ask. So one thing that you mentioned almost at the end of the presentation, when you're comparing different matrices and also like different PIM systems, is that there is no best number of vertical partitions. There is no one size fit all. My question here is, do you think it would be possible to try to design some sort of heuristic or maybe even machine learning based approach to come up with the best configuration, either a number of vertical partitions or others? And or if that's not the case, if that's not possible, at least would it be possible to have, I'd say, a compromise solution? You said there is no one size fits all, but maybe there is one. You have identified like some numbers that are usually good or somehow close to the optimal.
Yeah, thank you for the question. It's a very nice question. So actually, I believe that identifying the number of vertical partitions can be done very easily because machine learning is typically used whenever we have to solve complex problems. But this problem is not that complex. We can estimate the number of vertical partitions and the performance using simple analytical and statistical models. So I will elaborate this approach. Okay, so here we split the SpMV execution on 4 steps. So the only thing we need to do is to create some simple analytical and performance model for these 4 steps. The first step is like loading the input vector to the PIM-enabled memory. So it can be approximated as a linear function where the input is the number of bytes that we transferred from the host CPU to the PIM-enabled memories. And I'm pretty sure that there are many papers in the literature that have already estimated the performance overhead in the memory bus bandwidth. Next, we also need to create a simple performance model for the SpMV execution. And this can be simply identified after we do the partitioning. We can just simply identify the PIM core that has the highest number of non-zero elements, because that is the core that determines the execution time of the kernel time. And then the kernel time can be approximated as a linear function based on we give the number of non-zero elements, and the output of this function is the cycles or the execution time. And yeah, and the weights of the function can be extracted using some statistical modeling. And yeah, similarly for the retrieve and the retrieve time can be also approximately in a similar way as the load time. And finally, the merge step is like a simple reduction step on the whole CPU. And yeah, in the 1D partition kernels, it is like 0, so it's very easy to consider that negligible. For the 2D partition kernels, it can be approximated based on the number of vertical partitions. That the number of vertical partitions shows how many results that we need to merge in order to assemble the final output vector. Yeah, so I think that a very good follow-up work would be to create some wrappers in the Sparse P library, and we have like after we have different data partitioning, those wrappers are approximating they approximate the execution time of each data partition technique, and then we dynamically select the best SpMV execution of the Sparse P for its matrix.
Okay, yeah, I think the answer makes perfect sense. I also ask you if there are any, like, say, default values that you would use for configuration. I don't know if somehow, maybe, for example, in the repo, those are the default ones, or
I think that we can simply group the matrices, and based on the pattern of the matrix, we can approximate them. As I mentioned, in the regular matrices, typically we use 2D partitioning. So if for example, we know, or the user can tell us that the matrix is like a regular matrix, it doesn't have a power law distribution, we can just directly pick the 2D partition technique, the equally sized 2D partition technique, which is like the first scheme that I have here in this slide, the equally sized, sorry. Okay, so for the regular matrices, we can simply pick the equally sized 2D kernel, because more or less we have high balance across the PIM cores because the matrix is regular. And if we know that the matrix has a power law distribution, it is a scale-free matrix, the one that I saw in the right plot, we can simply select the 1D partition kernels based on the results that we have until now. The 1D partition kernel provides the best performance on the scale-free matrices, and also, as I mentioned, the Q format, because the CSR format is needed to perform the load balancing in a raw granularity. Yeah, so I mean, if we have like some insights, like hints about the matrix, we can simply select the correct scheme.
Okay, yeah, that makes sense. If you have a certain knowledge of the characteristics of the matrix, then it's relatively easy to find what a suitable configuration is going to be. Okay, yeah, that makes sense. Thank you, Christina. I have a couple more things that I would like to discuss with you. So one thing we know from this AppMem system is that it doesn't allow communication across different PIM cores, direct communication across different PIM cores. So any sort of communication or merging results step should happen on the CPU. So, however, there are other processing in memory architectures that enable some sort of communication in different ways, but it's something that it's certainly possible. So, how could your implementations change if it was possible to at least communicate, let's say, across, between the PIM cores inside the same chip? Do you think that that could change your implementations in any way, or is something that would be necessary to explore?
Okay, great question. Yeah, I think that in that case we can have like a slightly different data partitioning scheme. So first we need to do a data partition across the chips, not across the cores, because within the chip we have a connection. In that sense, we can. I mean, the basic implementation that we need is like we give the number of PIM cores and we do the data partition. In that case, we need to give the number of chips and we will do the corresponding data partition. And then within the chip, since there is communication, I believe that the internal kernel time, the source code that we have written for the PIM core that accesses the data from the local DRAM bank needs to slightly change because you can also access data across the PIM banks. So in that case, we need to give the corresponding remote location. Yeah, use the corresponding API that would be supported. So I believe, yeah, so I believe the host code that we wrote related with the partitioning will not change. The only that we need to change is the input that we give. But the kernel time of the PIM core needs to be slightly modified.
I see. Okay, yeah, that's good to know and makes perfect sense. Okay, one last thing I have here is you mentioned fine-grained logs, for example. You tried to use fine-grained logs and compare them to the coarse-grained logs, and apparently, even though the fine-grained logs, they enable much more fine-grained access and less contention when accessing the logs. But in the end, the problem is in the access to memory, right? That's what you explained, and it's because of how this specific processing in memory system accesses memory. So, but even though I think that there are similarities between the existing processing near memory systems that are placing compute elements near the memory banks, and they share like certain characteristics, but yeah, some of them, for example, right now I remember FinDRAM uses, I mean, it places one compute unit near two banks, which means that you can access both banks in parallel. And there might be other ways of increasing memory level parallelism. So in those cases, what would you expect for this workload, and in particular for the fine-grained and coarse-grained logs?
Yeah, that's a very good question. So the first thing that we need to do in that case is that to explicitly partition the data across the DRAM banks in order to know which elements of the output vector are in the first and which elements of the output vector are in the second bank. And in this way, we can implement fine-grained logging approaches where we have a higher execution parallelism, because we can access like the different DRAM banks concurrently. However, even in that scenario, I also expect that the execution parallelism will be double. Here we have like a serialized, and in that case, in the best scenario, we have two different critical sections to be executed concurrently. Because my insight is that locations, the DRAM bank can be accessed like as a transaction. So we cannot access the same DRAM bank, different locations, different rows of the DRAM bank concurrently because of the internal security of the DRAM, and we need to activate each row, one row at each time. Yeah, so in that case, I think that the performance might be improved, but it will not be like a linear speed up over compared to the number of threads. It will be like 2x. I mean, the parallelization, the parallelism that it is exposed is like how many number of DRAM banks we have local to each PIM core.
I see. Okay. Yeah, I hope hardware will keep improving, and we will have more the ability to exploit more memory level parallelism also for the individual PIM cores in future systems.
Yeah,
Mhm.
and one more comment that I would be interested is that in an architecture where we have like two different DRAM banks for each core, it might be feasible to have like some overlapping of the computation and the data transfers. So, for example, while the host has just enabled data transfer to the one of the DRAM banks, the PIM core can concurrently access data on the second DRAM bank and does computation on the second DRAM bank. So in that architecture, we might have like solutions to enable overlapping of the data transfers and the computation.
Yeah, that's actually a good point, indeed. Is that what happens in FinDRAM, for example? Are you? I mean, I don't think so, right? I think in FinDRAM, at least what I remember from their paper is that the CPU gets blocked while the processing elements are computing. But yeah, I think that what you said makes sense. I guess it must be feasible to implement, and hopefully we will see this as well in the near future, because it's clearly something. At least these systems where we have a PIM-enabled memory that is not replacing the main memory, at least at this point, it would be very good if we could overlap some of these data transfers.
Yes, and the solution to implement this overlap would be like having two DRAM banks and yeah, the host accessing the one and the PIM core the other one.
Yeah, that makes sense. Okay, yeah, sounds very good. I have one last thing that I just recall as well. At some point, you also showed like the scalability results for a single DPU, changing the number of pin threads. And you mentioned it's like the best performing number of pin threads is something between 12 and 16 due to the relation with the number of pipeline stages of the pin core. Exactly, this is a slide. But is 12? Is it 16 or is it something in between? Do you see any variability here or?
Yes, so this depends on the load balancing scheme and where is the bottleneck. So, for example, in this the Delaunay matrix, which is the top left matrix, the performance for the CSR format, the gray one, the performance with 24 threads is slightly better over 16 threads. And this because in the scheme that we have, where we load balance the number of non-zero elements, the bottleneck is the row imbalance. So the performance is bottlenecked by the one single thread that processes a much higher number of rows. So in that scenario, if we increase the number of threads, the row imbalance decreases and we have like a better performance in that case. And so the particular pattern, the particular sparsity of the pattern determines the number of of the threads that gives us the best performance in this particular scenario. But yeah, we have observed that typically it's like from 12 up to 16 threads, and this yeah.
Okay, yeah, I think that's also a very interesting observation, because so far in our PRIM work as well, what we essentially observed was that the performance was essentially flat after 11 threads. However, I think it's a very nice observation that we see still some performance improvement due to improving load balancing a little bit by using more threads.
Yes, exactly.
Okay, yeah, that sounds very good to me. I personally don't have any additional questions. I also don't see any questions in YouTube. But yeah, I guess we can ask people to also contact you and contact us in case that they have additional questions and they want to discuss anything else with you about this work. Okay, yeah, thank you very much, Christina. It was a great talk. I hope you continue being very successful in your research after you graduate, and hopefully we will be able to read more papers of this quality.
Yeah, thank you so much, and thank you for the invitation today to present our work. It was a pleasure for me.
Yeah, it was really nice to have you here. Thank you, and yeah, until the next time. And thank you everyone for your attention. Thank you for joining one more lecture of our Processing in Memory course. We will have a new lecture next Thursday, hopefully with another invited speaker. Thanks everyone, and see you soon.